All right, everyone, welcome to this month's PCAST talk. So before we get started, just a little bit of news and highlights. So as you may or may not have heard, the PRIMA team completed the APEX site visit process in May. So we hosted the review committee at JPL in Pasadena. And we are now just in the stage where we're awaiting news about the official APEX selection, which we're hoping will occur early this fall. So we've heard that this is planned to sort of occur before the end of the NASA fiscal year. I'm just sharing with you all a little team video that was made as part of the process.
Prima, geht voran.
Alle prima! Alle prima!
To get folks together from all of the various collaborating countries and institutions, and we're all really looking forward to hearing about the results of selection this fall. So the PCAST series will be continuing again throughout the fall. So we have a couple of upcoming talks this fall, more on the PI science. So we'll hear in October from Andrea Benzatti, who will be talking about the protostellar disk science. And then in August, we will also be hearing from Irene Shivai, who will be talking about some of the dust and metallicity science. And so we're going to hear some more about that today in the local universe. So today's speaker is Bogdan Pastrav, and he's going to be talking about dust properties in nearby galaxies and sort of the direction that is going for future work with PRIMA.
Okay, thank you, Elizabeth. As Elizabeth said, my name is Bogdan Pastrav. I'm coming from the Institute of Space Science in Bucharest, Romania, and I'm going to talk about today about relations between dust intrinsic properties, star formation, and some galaxy global and integrated quantities in nearby galaxies. This is a short outline of my talk. I'm going to mention the motivation for this work that I've been doing recently and a short introduction. Then I'm going to present the two methods. One method is for a derivation of star formation rates. And then another method to derive the dust temperature and the dust emissivity. Yeah, so in the next section of my presentation, I'm going to present the most important results with a few star formation scattering relations that were obtained with this method, and also some implications for PRIMA, and then the other relations that are connected with the dust temperature and emissivity indices, also metallicity, and a short analysis of these relations and implications for dust properties and other important ISM quantities. And I'll finish with some conclusions and some I'll talk about some future work, maybe including things related to PRIMA. This is the motivation for this work. Basically, this study that tries to determine dust temperatures and emissivity indices, it's a continuation of the work done in the past few years. The first, I was saying that the first part of the study was in 2020, back there, where I tried to study dust effects on these scalar relations in nearby galaxies on a sample of a well-known sample taken from Sphinx and Kingfish galaxies. And in that sample, I also derived the dust masses that I'm going to use further here to derive the dust temperatures and dust emissivity indices. And this work also relies on the paper in 2024, where I used the same sample of galaxies to derive dust-corrected star formation rate using a self-consistent method, and also study other dust star formation ISM scaling relations. It is known that dust, ISM, and star formation scaling relations are very important, quite essential in studies of galaxy and ISM evolution. But also it's known that most of the star formation ray tracers are affected and biased by dust and also other effects. And as galaxies can be in different star formation stages and ISM properties, one needs a good star formation rate tracer to derive accurate star formation rates and avoid any, as possible, any issues and biases. So as I said, consistent star formation rate tracers are needed. In 2024, as I was saying, I derived star formation rates, intrinsic ones, for the same sample of 24 galaxies taken from Kingfish and Things survey using H-alpha images. I've done a structural and photometrical analysis of the images to derive all the photometric and structural parameters of these galaxies. This was done as a case study on a well-known sample to show that the method works and is consistent with other results for the same sample. After this, and the second part of the study, more recent results, I tried to determine accurate values for the beta, which stands for dust emissivity index, and dust temperature for the same sample that I used before, based on previous work prescriptions, and as I was saying, the dust masses previously derived in 2020. Another goal of this study was to study the well-known beta dust temperature degeneracy, which appears in many similar studies. And as we know, there are various methods to determine these parameters, which also try to avoid this degeneracy. There is also a debate in the literature about keeping a beta a free parameter or taking it fixed to a value of 2 or 1.5. So here it's a lot of debate as well. And another goal was to basically just investigate this relation to see if there are any traces among the star formation quantities that would be used as a proxy to derive dust temperature, and study connected relations between sigma d, which is dust surface density, metallicity, and also implications for star formation rates and other parameters. As a last goal was to study which relations are fundamental and which correlations are stronger from all this. I'm going to start first as a summary quickly with the star formation rate method determination. Basically, as I was saying, I started with this sample of 24 galaxies, analyzing H-alpha images of spirals and S0 galaxies. I've done a photometry using the curve of growth method and a structural analysis using Galfit, deriving afterwards the luminosity for the H-alpha line and using it as a star formation rate tracer. It is known that H-alpha is a tracer for a very recent star formation rate, less than 10 mega years in the past. And from this, I derived observed star formation rates, specific star formation rate, and related parameters. The observed star formation rate was derived using this relation from Jimenez Arteaga, 2022, where I use this calibration and the H-alpha luminosity. I needed also the dust opacities, which were derived for the H-alpha line using an empirical correlation found by Grotes in 2013 between the dust opacity, central face-on dust opacity, and stellar mass surface density. And this is the second relation here, as you can see on this slide. While the dust masses were derived considering a specific star dust geometry from the Popescu 2011 model and the dust model of Drain 2003, which was needed for certain parameters like KH alpha, and this model of Drain, the characteristics of the model are embedded here in this constant K. After this, I used dust and inclination effects corrections, which I determined some time ago to derive intrinsic structure and photometric parameters, which were later needed for star formation rate and dust ISM scaling relations and their associated parameters. So from all this, I derived the dust corrected H alpha luminosity using this relation, taking into account the dust opacity, which I derived through this relation that I showed earlier, and having now the dust-free H alpha luminosity, I derived the corrected star formation rate, so devoided by dust effects, and also the associated parameters like specific star formation rate and star formation rate surface density, which was needed for certain relation. And just to give you a few examples of these relations obtained with this method, the most well-known is the, basically the star formation main sequence, which is in the first plot here. As you can see, I got quite a good fit, and a slope of 0.69, which is quite in a good agreement and consistent with other values in the literature, like Hunt et al. For low-Z kingfish galaxies, values from Elbaz, which got 0.77, Gavazzi, and so on. And really low scatter, not extremely low, but 0.39. Connected with this is the second relation in the second panel between the specific star formation rate and stellar mass, and the downward trend was recovered. It's an anti-correlation with a parameter with a slope of minus 0.31 and correlation coefficient of minus 0.48. So not such a strong relation like stellar star formation main sequence, but the parameters were quite consistent with other values in the literature from Hunt or Gavazzi. As one can see here, I put some numerical values. And the third panel stands for the result, the so-called result star formation sequence between star formation surface density and stellar mass surface density. And one can see that I got quite a good tight relation for this small sample of nearby galaxies with a slope of 1.03 and a strong correlation coefficient of 0.79, which is consistent with the other values, most of the values in the literature within errors, of course. And this method could be used in larger scale studies of star formation and ISM evolution when H alpha imaging is available, like JPass, J+, which has a H alpha filter at 6,614 angstrom, or VLT Muse. This is just a few other examples of these relations obtained with this method. The first one is the relation between dust mass and star formation rate, which was to be expected because it is a relation that is derived from star formation main sequence and a very tight relation between dust mass and stellar mass, which was observed also by Grotes in 2013, De Vries 2017, and myself in the paper from 2020, and also Van der Giesen. The scatter is quite large for the observed values, so the relation is not so strong as the previous ones, and it's not a fundamental relation such as the dust mass versus stellar mass. It's not so tight. I've analyzed this in the paper. The second panel shows the relation between dust opacity and star formation rate. Again, it's a bit of large scatter, but it's a relation also found in other studies by Van der Giesen. And the last panel, it's a relation between the ratio between dust mass and star formation versus specific star formation. This was plotted since the dust mass versus star formation rate is known as a tracer of dust to gas ratio, and one can see it's a very tight relation with an anti-correlation with a slope close to -1, not so large scattering, and a strong, very high correlation coefficient of -0.86 for the observed relation. The reason for having basically two type of data points for each plot is because the black points stand for the observed measurements, which are not corrected for dust, and all the red ones and the fits, which were obtained from a linear regression fit, stand for the intrinsic relations or quantities, which were dust corrected. So as I was saying earlier, this star formation method and the values which derive star formation rates, very recent ones, in case you use H alpha fluxes, so less than 10 megayears old for those galaxies, could be used to compare with star formation rates derived from ACD feeds, which usually derive star formation rate about 100 to 500 megayears in this period, and hopefully these values will be available with data coming from PRIMA, so data from mid-infrared to far infrared to derive, basically do ACD feeds and derive star formation rate and in this range, and compare with results from this H alpha imaging method for the galaxies where H alpha imaging is available. Now I'm going to back to the slides related to the method for the dust temperature and dust emissivity index derivation. So as I was saying, the dust temperature are determined based on galaxy dust masses for the same galaxies, which are derived earlier. Again, based on, as I was saying, based on Grote's 2013 correlation, the dust model of Drain 2003, and this Popescu 2011 stardust geometry. And the relations are here. This is the first one is the Grote's 2013 empirical correlation, and the other one is the relation between dust opacity and the dust mass. And here, this is the scale length. R SDB stands for the scale length of the stellar disk in the B band. It is known in the literature that one of the methods to derive dust masses and other parameters, it's an ACD fit of a cold dust emission using either a modified black body, one component modified black body, or two modified black bodies, one for each dust component, one for the cold dust and one from the warm dust component. Or there are the other methods using radiation transfer codes. And the main goal of these methods is to derive all these parameters like dust temperature, dust masses, beta, and star formation rate. And I put here a bunch of references that are relevant for this work. I put in red the dust mass and star formation rate because in my case, I already knew these values, and all I have to do was to derive only the dust temperature and beta. As I was saying, in the literature, there are also many issues with the degeneracy that appears in between beta and dust temperature, and the fact that one needs fluxes at multiple frequencies to actually do an ACD feed of the cold dust emission. So my method is not quite complicated. It's just using a self-consistent method. I consider, like other people, one component modified black body to describe the cold dust emission ACD from the infrared to some milliliter. But I only use the flux of 250 microns, which samples quite well the peak of the cold dust ACD, but I have, without performing actually an actual ACD fit of the whole range of near infrared to far infrared submillimeter fluxes. This is a problem because sometimes for some galaxies, you don't really have all the needed fluxes, so one cannot do a good SED fit if you don't have all the fluxes. So I use this flux of 250 microns, and the constant K nu, the reference one, that lambda 0 100 microns taken from Drain 2003 model. Other people use other reference wavelengths from 100 microns up to even 500 microns in the literature. So basically, I consider two scenarios because I want to compare what happens with all the parameters and all the relations when beta is a free parameter, and then, as in many studies in the literature, when beta is fixed to a value of 2. So I started with basically I did like a grid search without considering a specific value for beta a priori. So I started with a range of values for constant K nu from 0 to 10 square meters per kilogram in steps of 0.05, while for the dust temperature I went from 0 to 80 kelvins in steps of 0.1 kelvins, and I try to derive the best fit for the dust temperature, the best fit value, which minimizes the differences between M dust derived from previously Pastrav 2020, independently of the dust temperature, and the second value of dust temperature derived from this equation 1 here. As you can see, you can extract dust mass using the flux at 250 microns, and this is the black body function, and the others are the quantities that I explained earlier, beta and the reference frequency, and d is the distance to the galaxy. So basically I derived this the dust temperature, which minimizes difference, and from this simultaneously I derive the best fit value for the constant K nu. And using equation 2, I derived in the next stage the best fit value for the dust emissivity index is beta for each galaxy. So I was saying it's similar with a grid method to derive these two parameters without prior assumptions about beta. As a side calculation, I also derived the dust disk scale lengths and dust surface densities, which are needed later for some specific relation. It is known that in the literature that beta usually has values between 0.8 and 2.5, and that beta is has a strong connection with dust grain properties. If beta has high values, this is specific for cold dust, 10 to 25 Kelvin. If beta is lower, then it's specific for warm dust. It hasn't been observed any conclusive trend with the redshift. For example, Bendo 2023 and 24 has not observed this. But beta varies within galaxies because we have different dust components. In the literature also has been observed that this degeneracy between dust temperature and dust emissivity in this index. And some people explain it because of noise and using one component, modified black body, or considering basically only one dust temperature, which is basically an average dust temperature along the line of sight, because obviously galaxies have dust distributions with various composition and dust temperature. But even so, this method used by in many studies has managed to output meaningful results for the dust properties. I think something is wrong here with my slides. Just a second. Okay, that's it. Yeah, and in this table of plots, I'm showing a few relations. It's a comparison between some relations on the upper row you obtain when beta is a free parameter, and on the lower row of plots, they are the same the relations obtained when beta is fixed to a value of 2. In the first column, it's basically the relation between metallicity taken from literature and dust temperature. It's between dust temperature and dust surface density, as this is the only relation where something changes. Basically, the trend is reversed when going from a free beta to a beta equals 2. And the other two relations are between dust temperature and star formation rate and the specific star formation rate. And only in the third column of plots one can see that, star formation rate can be potentially a good tracer. A specific star formation rate can be a good tracer of dust temperature. But I'm coming back to this relation in the next slides. So as I was saying, if beta 2 is fixed, this does not change significantly the results when compared with beta is free, except for that relation that I mentioned earlier. Now, in this slide, I'm presenting the evolution of dust temperature with beta, which is in the first plot here on the left side. Both the observed and corrected relations. As one can see, I still recover this curve relation between these parameters, which means that even when using dust temperatures derived independently, so not from an SED fit, so independently of dust temperature, I still get sort of degeneracy between these parameters, which couldn't be avoided apparently. For this study, I also derived the average values for dust temperature, and the values that I got are quite consistent with other studies. For example, I got an average value for the whole sample of 20.89 kelvins, only for the spiral galaxies. And if I include the S0s, this goes a bit higher to 22.6 kelvins, which, as I was saying, is quite consistent with other values for the same sample or nearby galaxies. If from a log linear fit of this relation, one can get a slope of minus 0.72 for observed relation or 0.90 for the corrected one. And this also is an agreement with other studies. If beta is fixed, the values are systematically higher. The average values, for example, dust temperature is 27.59 for the spirals and even 30.51 for the whole sample, including S0 galaxies. Now about beta, again, I derived average values to compare with other studies in the literature, and I got 1.64 for the observed values, taking into account all the galaxies in the sample, and a bit lower for the corrected one. And this is, if I consider only the spirals, the values are slightly higher. The average values are 1.70 and 1.39. And as I was saying, this is consistent with errors with other studies which I mentioned here. I got an interesting relation between dust surface density and dust emissivity index, which could be expected. It's a relation between an intrinsic property of dust and a more global one, which is the dust surface density. The relation is not very strong. The correlation is 0.44, and it shows that dust with higher percentage of silicates in galaxies is usually found in more compact dust distribution. This is what this increasing trend tells us. This is the relation from the second panel. It's true that the scatter is it's a bit high, but maybe with a higher sample, this could be reduced. And in the last panel, it's a well-known relation between dust mass and metallicity, which was expected from well-known mass metallicity relation, well studied in the literature. There were other relations that were observed in the literature, but I haven't seen any correlation here, such as the relation between beta and stellar mass or stellar mass surface densities, which were observed in studies from Cortese 2014 or Lamperti, but here these were not obvious. They were not conclusive results. Here it's an interesting plot. I'm continuing with the result from this study. This is the relation that I showed earlier, but here I'm overplotting something. So it's in the first panel, I'm showing the relation between dust temperature and the specific star formation rates. As you can see, it's an increasing trend. And I'm overplotting the dust temperature obtained using the empirical relation from Manieli 2014. Basically, I used my specific star formation rate and I derived with their relation the other values for dust temperatures. And this is the trend here. It's a linear trend. It looks a bit shifted from what my results, a bit upwards, but the trend is also increasing. So basically the dust temperatures are increasing with the specific star formation rates, and this means that this could be a potential tracer for dust temperature. And the second plot, I'm showing the relation between dust temperatures and metallicities of the galaxies. And one can see, even though there's a bit of scatter, it's a decreasing tendency, which means that metal-rich galaxies tend to have colder dust in general. And this gives us information about grain composition and properties. And this relation also was observed in Rémy-Rouillet 2013 or Cortese, while studies like Lamperti 2019 found a flat trend. And the last plot for this slide is another relation between dust emissivity index and the metallicity. This time this trend that I got is a bit shallow, quite shallow, and the slope is really low, like 0.25, with a correlation coefficient of 0.52. But this relation has been observed in other studies, which I mentioned here. And this tells us that metal-rich galaxies have a dust with grain composition more abundant in crystalline silicates. This is what this relation should tell us. Here it's a few other relations, some of them important. I'm showing here relations between the dust mass surface densities and other related parameters. In the first plot is the tightest relation between the dust surface density and stellar mass. It's the strongest correlation and lowest scatter. As you can see, I got a correlation coefficient of 0.89 for the observed correlation and 0.81 for the corrected one. And this can be taught as a result of the tight dust mass versus stellar mass relation, which some other people have shown, including myself. In the second plot, one can see another correlation between stellar mass surface density and specific star formation rate. It's a downward trend with a slope of minus 1.01 and a correlation coefficient mild one, minus 0.59. The relation between the dust mass surface density and star formation rate is not so strong, as you can see in the third panel, and the scatter is a bit high, but again, maybe this can be reduced with a larger sample of similar galaxies. And this, from all these studies, I concluded that star formation rate or star formation and surface density are not conclusive tracers of dust temperatures, but only there is the specific star formation rate can be, as I shown earlier. It's important to mention that I noticed a flat trend between the dust mass versus stellar mass, the ratio between dust and stellar masses versus metallicity, and also with dust temperature. Some other people have observed an increasing trend, like Rémy-Rouillet, but I think this is important to correct for dust effects. And basically, I think what I noticed that the trend is basically flat, like I'm showing here in the last plot. This goes to show that it's important to apply dust corrections. I think it's the second last plot. Sorry. Yeah, these are a pair of plots, a few other plots. And the second panel is the relation between the star formation rate and beta. I investigated to see if there is any correlation between this, as expected to be one from other relations like dust mass versus stellar mass. Sorry, dust mass versus the star formation rate, or the dust opacity versus star formation rate. And I could see here in the second panel that galaxies with higher star formation rate and of course more dust mass have dust with higher beta, so more silicates present in their grain composition. So basically, you get lower dust temperature if this anti-correlation between beta and dust temperature is valid or real. In case of the relation between specific star formation rate and beta, I got a mild anti-correlation between these two with this derived values of the slopes, which you can see here, and the mild scatter of 0.3 dex. I'm going to jump to the next slide. Yeah, this plot that shows the scale length of the dust disk versus the scale length of the optical disk, or the optical stellar disk in the B band. And one can see here a linear increase between these two scale lengths, which shows that dust disk extent increases monotonically with the stellar disk 1. And I got a slope for this relation of 0.59 for the observed relation and 0.55 for the corrected one, corrected for dust effects. And this is consistent with other studies in the literature, like this one from Kin. You got a slightly higher slope, and also Mosenkov, but they basically derived this K length for other wavelengths. So this comparison would be even more meaningful if we would have the same wavelengths. But it's also interesting to see this evolution. And now I'm going to the conclusions and future projects. So I basically use this method to derive dust temperatures as a case study to show the validity of the whole equations and method and a well-studied sample that I used before. And this could be extended to larger scale studies of nearby galaxies or even mid-redshift. The other set of equations and method for the star formation rate and the values, as I was saying earlier, could be as a means to compare with results from SED feeds using future data from surveys such as PRIMA. I got consistent dust and temperature and dust emissivity index values derived from one modified black body fit and these dust masses, and without actually doing the calculations and doing a complete SED feed of the cold dust emission. And I'm still working on this. The warm dust property is important to say. If you use a two-component dust model, we'll be able to be tightly constrained with a survey such as PRIMA because of the large photometric coverage at 24 to 235 microns. So then we'll be able to use the component models more confidently and constrain the dust properties. I will observe that keeping beta fixed to a value of 2 does not change significantly the results. Most of the scale relations are consistent with other relevant studies and their specific parameters. Yes, only the specific star formation rate can be a potential dust tracer, dust temperature tracers, as I shown in the previous plots. Some of the relations are not conclusive, or maybe because of the insufficient data or not enough statistics. I also seen some interesting relations, such as the one between dust surface density and beta, which I haven't actually seen it in the literature. So it tells us something interesting about dust properties. And yes, this is basically what I wanted to say, and try to make a bit of connection with future data coming from PRIMA, which will be very useful in the mid to far infrared, and to basically compare the results and for the star formation rates, and even to constrain better the dust properties, especially the warm dust properties. Thank you.
Thank you. All right, we have time for folks to ask questions. You can go ahead and raise your hand on Teams, or you can also type your question into the chat.
I think
So thanks so much for talking about some of the things you would be interested in doing with PRIMA. I know one of the big advantages is, of course, its sensitivity. So can you say anything about sort of like what sort of sample sizes you might want to do with PRIMA compared to what has been previously done?
as I was saying earlier, my sample was quite small, like about 30 galaxies. So obviously, I want to extend this to a few, maybe 2 orders of magnitude, probably. And I think PRIMA would be able to deliver data for such high samples at even higher redshifts, not only for nearby galaxies. And this, of course, would help for better statistics for this study, but also for other similar ones, trying to derive self-consistent and accurate star formation rates, and even dust properties, I mean, important parameters for the dust, which are not so well constrained. And this is a known problem in the literature, both within galaxies, but like beta, but also for higher samples, and to see important variations of these parameters and try to understand why this happens and how these dust properties change with the environment and with redshift.
Thanks.
I think there is something.
Question in the chat. Yep.
Let me see if I can open it.
Yes, we have it says, thanks for the talk. I'm wondering if PRIMA may help to better constrain dust composition and its effect on beta.
For sure, it will be able to constrain it. Being such a, I mean, having such a, important sensitivity, especially for the range of wavelengths that we are interested, from mid-infrared to near to far infrared. Obviously, we will have more available data. We could do better ACD fits of the data, having more fluxes in that. I mean, that range of wavelengths will be much better sampled, so you will get better ACD fits and be able to constrain a lot better these dust parameters like beta and dust temperature, and even go to more complex models, not only one modified black body, 2 modified black bodies, and we could also use some submillimeter data to also constrain the Rayleigh Jeans tail of the ACD, and this will also impose better constraints on beta, all in conjunction with the PRIMA data. So I think this will be quite important when we will have this data for PRIMA. I'm not sure if this answers to the question.
Thank you. All right, we have time for maybe another last question. And our previous question asker said thank you. Yep.
Oh, I've seen it now. Yes, I can see now the window, the chat window.
All right, well, thank you so much for your talk today, Bogdan. Thank you everyone for joining us. Again, the recording will be made available on YouTube for folks who want to catch this or other talks that they missed, and we'll see you next month.